Welcome to our comprehensive exploration of engineering mechanics. Today, we'll dive deep into two fundamental concepts that form the backbone of mechanical and structural design: structures and friction. Let's talk about trusses, the unsung heroes of structural engineering. A truss is essentially a lightweight yet incredibly strong framework composed of triangular units. Think of it like nature's most efficient load-bearing design. These structural marvels are primarily used in bridges, roofs, towers, and countless other engineering structures. What makes trusses special? They transfer forces brilliantly through axial tension and compression. By using triangles, the most stable geometric shape, engineers create structures that can bear enormous loads while remaining surprisingly lightweight. Imagine a bridge that can support heavy trucks or a roof that withstands extreme weather. That's the power of a well-designed truss. Now, let's zoom in on plane trusses, the two-dimensional cousins of our truss family. A plane truss is a flat, interconnected framework made of structural members forming triangles. The magic of these structures lies in their ability to distribute loads effectively and resist deformation. Why triangles, you might ask? Because a triangle is the only geometric shape that cannot be deformed without changing the length of its sides. This inherent rigidity makes triangular trusses incredibly stable under external forces. In a plane truss, each member is designed to experience only axial forces, either pure tension or pure compression. It's like a perfectly choreographed dance of structural elements working together to maintain stability. Let's explore the concept of a perfect truss, a mathematical marvel of structural engineering. A perfect truss is precisely balanced, with just the right number of members to ensure stability and rigidity without any redundancy. It's like a perfectly tuned orchestra where every member plays a crucial role. The key to determining a perfect truss lies in a mathematical condition. The number of members must equal 2 times the number of joints, minus 3. Let me break this down for you. Consider a truss with 5 joints. By applying our formula, we'd need exactly 7 members to create a perfect, stable structure. It's a delicate balance between having too few members, which would make the truss unstable, and too many, which would complicate the design unnecessarily. Now, let's discuss imperfect trusses, structures that deviate from the perfect balance. There are 2 types of imperfection we need to understand. First, we have deficient trusses, where the number of members is less than what's mathematically required. These trusses are like a house of cards, unstable and unable to resist external loads effectively. On the other hand, we have redundant trusses, which have more members than necessary. While it might seem like more members would make a structure stronger, in reality, these extra members can complicate the analysis without providing significant structural advantages. Think of it like adding extra wheels to a bicycle. It doesn't necessarily make the ride smoother or more stable. When analyzing trusses, engineers rely on several critical assumptions to simplify complex structural behavior. First, all joints are considered pin-connected, allowing rotation but preventing translation. Imagine a flexible joint that can pivot but not slide. Second, all external loads are applied directly at the joints, which helps avoid creating bending moments in the members. Third, members are subjected only to axial forces, pure tension or compression. And finally, the weight of the members themselves is typically negligible or assumed to be applied at the joints. These assumptions transform a potentially complicated analysis into a more manageable statics problem. It's like creating a simplified model that captures the essence of the structural behavior without getting lost in unnecessary complexities. Let's dive into the first method of truss analysis, the method of joints. The method of joints is a fundamental approach to truss analysis, focusing on the equilibrium of forces at each joint. By selecting joints with only two unknown forces and resolving them horizontally and vertically, we can systematically determine the axial forces in each member. This method is particularly effective for smaller trusses, providing a straightforward and systematic approach to understanding the load distribution within the structure. The core principle of this method lies in ensuring equilibrium at each joint, where the sum of horizontal and vertical forces must equal zero. By progressing through the truss, joint by joint, we can unravel the intricate interplay of forces and gain insights into the overall structural behavior. This methodical approach transforms a complex system into a series of manageable equations, making it a valuable tool for structural engineers. Welcome to the method of sections, a powerful analytical technique that takes a different approach to understanding truss behavior. Instead of examining each joint individually, this method involves strategically cutting the truss into sections to analyze specific parts of the structure. Imagine taking a slice through the truss to reveal its internal forces. The key here is to apply equilibrium conditions to the entire cut section, balancing forces in all three directions: horizontal, vertical, and moment. This method becomes incredibly useful when you want to determine forces in specific members without analyzing the entire truss. It's particularly efficient when you need to focus on critical members in complex structures like bridges or large industrial frameworks. Think of it as a surgical approach to structural analysis, precise, targeted, and incredibly informative. Let's explore the graphical method, a more visual approach to truss analysis. Unlike purely mathematical methods, this technique allows engineers to literally draw out the forces at work. The process begins by drawing the truss to scale, then graphically representing loads and reactions. By constructing a force polygon, we can determine the forces in each member visually. It's like creating a picture of forces, where the geometry of the drawing reveals the structural behavior. While this method might be less precise compared to analytical approaches, it offers an invaluable tool for visualization and approximate solutions. Engineers often use this method for quick estimations or to gain intuitive understanding of force distributions. Imagine being able to see the forces flowing through a structure. That's the power of the graphical method. Truss analysis isn't just a theoretical exercise, it's a critical tool in real-world engineering. In bridge design, engineers use these techniques to determine precise load-bearing capacities and identify which members are experiencing critical tension or compression. Building structures rely on truss analysis to design robust roof frameworks that can support various loads efficiently. Transmission towers, those towering structures that carry electricity across vast landscapes, depend on truss analysis to ensure stability against wind and environmental challenges. Each application demonstrates how understanding truss behavior translates directly into safer, more efficient infrastructure. From the bridges we drive on to the towers that power our cities, truss analysis is the invisible engineering that keeps our world standing strong. Let's dive into the fascinating world of friction, a fundamental force that shapes how objects interact and move. Friction is a resistive force that opposes the relative motion or tendency of motion between two contacting surfaces. It's not just a theoretical concept, but a critical phenomenon that affects everything from the shoes we walk in to the most complex machinery. At its core, friction arises from the microscopic irregularities on surfaces and the intermolecular forces at points of contact. Imagine two surfaces trying to slide past each other. The tiny bumps and valleys create resistance. In engineering, Understanding friction is crucial because it determines how machines work, how components interact, and how we design systems to move efficiently or stay stationary when needed. Let's talk about static friction, the unsung hero that keeps things from sliding around unexpectedly. Static friction is the force that resists the initiation of motion between two bodies when they're at rest. Picture a book sitting on a slightly tilted table. Static friction is what prevents it from immediately sliding down. What makes static friction unique is its dynamic nature. It increases as you apply more force, up to a maximum value. Once the applied force exceeds this threshold, motion begins, and static friction transitions to kinetic friction. It's like a protective barrier that gradually gives way under increasing pressure. This type of friction is crucial in countless applications, from preventing your coffee mug from slipping to ensuring the stability of structures and machines. Now we transition to kinetic friction, the force that comes into play when surfaces are actually moving relative to each other. Unlike static friction, kinetic friction is a constant force that opposes the relative motion between two bodies. Imagine sliding a book across a table. The resistance you feel is kinetic friction. Here's a fascinating characteristic. Kinetic friction remains constant for a given pair of surfaces, and interestingly, it doesn't depend on the velocity of motion. It's generally less intense than static friction, which is why it's often easier to keep an object moving once it's already in motion. This type of friction plays a crucial role in everything from mechanical design to understanding how objects move and interact in the real world. Let's unpack the fundamental laws that govern dry friction. First, there's the law of proportionality to normal force. The frictional force is directly proportional to the normal reaction force. This means the harder two surfaces are pressed together, the greater the friction between them. Second, and perhaps surprisingly, friction is independent of contact area. The microscopic contact points determine friction, not the overall surface size. Third, friction depends entirely on the materials and their surface conditions. Different materials will create different levels of resistance. Finally, and this is crucial, static friction is always higher than kinetic friction. This explains why it's often harder to start an object moving than to keep it moving. These laws might seem simple, but they're the foundation of understanding how objects interact in mechanical systems. Enter the coefficient of friction, a dimensionless quantity that quantifies the interaction between two surfaces. We have two types, static and kinetic coefficients. The static coefficient applies when an object is at rest, while the kinetic coefficient comes into play when the object is in motion. Let's look at some real-world examples. Rubber on concrete has a high friction coefficient of about 0.8 when stationary and 0.7 when moving. In contrast, ice on ice has an incredibly low friction coefficient of around 0.1 when stationary and just 0.03 when moving. This explains why it's so challenging to walk on ice. The surfaces have minimal friction. Understanding these coefficients is crucial for engineers designing everything from footwear to industrial machinery. The angle of friction is a fascinating geometric representation of how friction works. It's defined as the angle made by the resultant of the normal reaction and the limiting friction force with the normal force. The formula is beautifully simple. Tangent of the angle equals the coefficient of friction. As the coefficient of friction increases, so does the angle of friction. Think of it like a visual indicator of how sticky two surfaces are to each other. This concept is more than just mathematical. It helps engineers understand how surfaces interact and predict movement under different conditions. It's a key principle in designing systems where friction plays a critical role, from mechanical bearings to understanding how objects might slide on inclined surfaces. Let's explore the angle of repose, a critical concept in understanding how granular materials behave. This is the maximum angle at which a body can rest on an inclined plane without sliding due to gravity. The relationship is direct. The tangent of this angle equals the coefficient of friction. Imagine a pile of sand. There's a specific angle at which it will remain stable before starting to slide. This principle has profound practical applications. Engineers use the angle of repose in designing sand heaps, embankments, and understanding the stability of geological formations. It's not just a theoretical concept, but a practical tool used in construction, mining, agriculture, and many other fields where understanding material behavior is crucial. Let's dive into the fascinating concept of the cone of friction, a geometric representation that helps us understand the limits of force application. Imagine a right circular cone whose axis aligns with a normal force, with a half angle at the apex equal to the angle of friction. This cone is a powerful visual tool that shows the range of directions in which a resultant force can act without causing sliding. Think of it like a safety zone for force application. When the resultant force remains within this cone, the body stays perfectly stationary. It's a conceptual way of understanding the delicate balance between applied forces and friction. This visualization helps engineers predict and design systems where precise force control is critical, from mechanical joints to stability in complex structures. Now, let's explore the intriguing phenomenon of frictional locking, a critical concept in mechanical design. Frictional locking occurs when friction prevents the relative motion of components in mechanical systems. Picture this: in bolted joints, press-fitted parts, or complex mechanical assemblies, friction becomes a powerful ally in maintaining stability. It's like a natural fastening mechanism that doesn't require additional hardware. Applications are everywhere, from ensuring the tight fit of machine parts to preventing undesired motion in precision mechanisms. Engineers deliberately use frictional locking to create robust, self-securing designs. It's a testament to how understanding friction can transform a potential weakness into a strength in mechanical engineering. Let's examine friction in flat pivot bearings, a classic example of how friction impacts mechanical systems. Imagine a rotating disc in contact with a stationary flat surface. The frictional torque in this system depends on several key factors: the coefficient of friction, the load on the bearing, and the radius of the disc. This relationship reveals how even a seemingly simple mechanical interaction involves complex force dynamics. The torque generated by friction can significantly impact the efficiency and performance of rotating mechanical systems. Engineers must carefully calculate and account for this friction to design machines that operate smoothly and with minimal energy loss. It's a beautiful example of how microscopic surface interactions can have macroscopic effects on mechanical performance. Our exploration of friction continues with flat collar bearings, another critical mechanical configuration. In these bearings, a collar rotates against a flat surface, creating a unique friction scenario. The frictional torque here depends on the inner and outer radii of the collar, along with other critical factors. This design is crucial in many mechanical systems where precise rotational control is necessary. Imagine the delicate balance required to minimize friction while maintaining structural integrity. Engineers must carefully calculate the interplay between the collar's geometry and the frictional forces. It's like a carefully choreographed dance of surfaces, where every tiny detail can impact the overall performance of the mechanical system. We conclude our journey with flat belt friction, a fundamental principle in power transmission. Flat belts are used in countless applications, from industrial conveyor systems to drive mechanisms in machines. The magic happens in a relationship between tensions on the tight and slack sides of the belt. The friction formula here reveals how the coefficient of friction and the angle of contact determine power transmission efficiency. It's a perfect example of how engineers harness friction as a useful force rather than just seeing it as a resistance. From power transmission in conveyor belts to drive systems in industrial machines, this principle is crucial. Our exploration of friction demonstrates how understanding these fundamental interactions can unlock incredible engineering possibilities. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.